further expand on this point, let me begin with a word of prayer before I have to edit something. Dear Heavenly Father, we thank you for this day, and I thank you again for this class. Just ask that you'd guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I'm going to resist the temptation to talk about Lie algebras just yet. I will talk about those later in the course, and we should let that happen when it happens, because if I do it right now, a couple things. Number one, like we don't have all of the background that we're going to bring to bear when we have that discussion in here. And the other thing is, I'm teaching this matrix groups course right now, and so like by the time we get to that lecture, I should have like all the best of hits to share with you guys in here from that course. And that way, you know, you won't have to suffer through the process of me learning how to do things again. Let Sam and Shane do the suffering, you know, and then you guys just get to reap, hopefully, the clear statement of how things work when we get back here. So what I wanted...
That's just Sam and Shane.
Yeah, at the moment. Yeah. So, yeah, we meet in the conference room down there, like Monday, Wednesday, Friday, whatever it was. 1-ish, 1:10, I think. All right, so we need to think about higher derivatives for a second, because in order to appreciate what I'm about to do, you need to appreciate what I'm not doing. And that's talking about higher derivatives in the way that we're forced to talk about them in a normed linear space. So like, first of all, let's think about the first derivative. How does the first derivative work? So if we have f, a function from, say, v, right, to w, where v and w are normed linear spaces, we defined the Fouché derivative. That was our notion of derivative, right? And so we had df. dfa was, how did that go? That was a mapping from what? From v to w again, right? Where, I mean, technically dfa is an element of the linear transformations from v to w, right? So like it's a linear transformation from v to w. Now that's not the derivative really though, right? Like that's the derivative at a point. So if you want to think about the derivative in the sense like we think about the derivative of e to the x is e to the x, right? So like the derivative of the exponential function is the exponential function, or the derivative of the x squared function is the 2x function, right? So in calculus, we take a function, we form the derivative at each point, and that gives us a new function pointwise defined by the derivative at the point, right? That notion here would amount to assigning for each a dfa. Like that's the analog of the first derivative, right? So what kind of thing is that? Like we're talking about a, you know, we're talking about a function from, well, I mean, I guess technically it's a function that has v as input and then like linear transformations as outputs. Like that's the kind of thing it is. It's a function from the normed linear space to linear transformations from the normed linear space to the, you know, the range. And then what, I mean, that is, so if I call this thing f prime for the sake of this discussion, right? Let me big F prime. And then you ask okay, well, I mean, you can view, you can then form the derivative of f prime, because after all, you know, we can look at, well, I'm messing something up here, but I feel like I've lost track of something here. So I say, well, here's what I have written in the notes. Let me just write it down because I don't want to belabor this here. So like f prime prime would be something like u maps to, and a u is just v. I'm just using v for u. So v maps to like linear transformation. Oh, fine. U. So I really should have made the domain of f a subset of v. All right. So like u goes to linear transformations. Where did I lost my place? Where did it go? Come back to me. U goes to linear transformations from V, taking its outputs in linear transformations of V to W. So it's like a linear transformation valued linear transformation of V. And so, I mean, you start having to look at things like this, f prime prime of A. You can think about it as taking in a pair h comma k, and that's something like dfa prime of h comma k, which you could view as the differential of h maps to df h of A at k. And this is just for like the second derivative. The thing is, here's the basic problem. As we differentiate, we don't have an object of the same type. I started with a mapping, for instance, let me make it more concrete for you guys. If I had, if I have function from Rn to Rm, right? Then essentially df is what? It's like, its matrix is a Jacobian, It's not one column vector, it's n of them, right? So the derivative is not the same kind of thing as the function you're differentiating, because instead of just having one m vector, you need n of them, right? Like, this is partial f partial x1, partial f partial x2, and so forth and so on, right? Partial f partial x n. Now, like, partial f partial x1 is maybe a mapping from U, a subset of Rn, to Rm, just like, f is a mapping from U, a subset of Rn, to Rm, right? So we can think about the partial derivative functions, right? But any one of those partial derivative functions doesn't tell the whole story of the change in the function. We need all n of them to capture the change. And this just compounds as we look at higher derivatives. It becomes more and more meta, because you need not a linear transformation, but like already it's a bilinear transformation for the second derivative. It's a trilinear transformation for the third derivative. It's an m linear, however many you m, let's say n. I don't want to use m or n. A k linear transformation if we have the kth derivative. Now, because partial derivatives commute, which don't worry, I will not prove in here this semester, relax. Because partial derivatives commute, you can assume that k-linear transformation is like completely symmetric. So the multilinear algebra of higher derivatives is like manageable, but also it's definitely not at the level of this course as I'm currently teaching it, all right? But that's what we're up against. That's why I only talk about first derivatives in here, rigorously. Yeah? So that's why what I'm about to show you about the calculus over an algebra is so interesting. Because if I have a way, I'm going to show you that for a function with a rather special property, which I'll call adifferentiability, we can actually define for a function that goes from an algebra to an algebra, I can also define a derivative of that function which goes from the algebra to the algebra, and a second derivative which goes from the algebra to the algebra. Like, all of the higher derivatives are, again, just functions on the algebra. And so that was when I finally realized that is so much of what makes the A calculus understandable and beautiful, is that it's just like regular calculus. But okay, before we do that, before I can talk about calculus over an algebra, look at that, I just popped that thing right off. Before I can, oh no, what did I just do? It's not good. Yeah, I know. I seem to have well, all right, we're okay. At least I didn't, I could have, oh, wait a minute, what's that? No, that's not me. I was worried I'd like snapped it, you know, but it's fine. Fun story, this mic cost me $15 whole, which is kind of an interesting story in a sense, because like when I bought it 4 or 5 years ago, it was $50, but the price went down to 15. Isn't that weird? It's the same model, the Movo 50, I think. But anyway. Okay, so before I talk about calculus over an algebra, I should at least spend 10 minutes describing to you guys what I mean by an algebra, right? So we say A is an algebra with multiplication, and I'm going to use star for this just for the sake of like discussion, but when we actually get into examples, I probably won't draw star. I'll just draw like, use juxtaposition for the product, but I think it's helpful to write the star for the sake of communicating like how it works. So like, what is an algebra? So if A is a vector space, and I mean vector space over the real numbers. I keep my algebras real, all right? So vector space over R with this multiplication, it's a mapping from the algebra across the algebra back to the algebra again. And it has to basically satisfy the usual laws of arithmetic. So like cx plus y times z, or x times cy plus z. You could tell me what these are, right? You can pull the constant out, and you've got like the constant times x times z plus y times z, and here you got the constant times x times y plus x times z. So like we have distributivity across addition on both sides, all right? And I also assume A is associative. So that means that x times y times z makes sense, in the sense that if I didn't write these parentheses down, it wouldn't matter. Right? It's an associative. That means associative algebra. Looking far ahead, when we talk about Lie algebras, Lie algebra is an example of an algebra which doesn't have to be, in fact, usually isn't associative. All right. Do you guys know any products that are not associative? There are 2 examples you should be familiar with. The one is subtraction. Right? If you think about subtraction, it matters which order you do it in. The other is the cross product. Like the cross product's not associative. Now the cross product paired with R3 actually gives us an example of what's called a Lie algebra, but again, for later. All right, so it's an associative algebra, and then I also assume A is unital, meaning there exists like 1 in the algebra such that 1 in the algebra times x is equal to x, but that's also, of course, equal to x times the 1 in the algebra, right? So like the algebra 1 multiplies with anything to give back the anything, all right? And if x times y is equal to y times x for all x and y in the algebra, then the algebra is commutative. I think all the examples I'm going to look at with you guys today are commutative. All right. So this is what an algebra is. And I also look at finite dimensional algebras. So for me, really, an algebra is a n-dimensional vector space. All right. So like typically, I'll think of A as just equal to Rn as a point set. But technically speaking, you could make the algebra, you know, a set of matrices or something else if you wanted. Okay, so definition, we can talk about like left multiplication. I let you guys pick. I'm trying to decide whether to use a capital L or lowercase l. Choices. Capital L it is. So left multiplication by, let's say, A is defining a mapping from the algebra to the algebra by left multiplication of x is equal to A times x, right? And let's continue to, let's, for the sake of simplicity today, let us demand that the algebra is, we're gonna just work with this. The algebra, all the algebras I'm going to think of concretely as Rn, all right? So, this is the so-called left multiplication. I can't spell. Well, let's just go with this, multiplication by A, all right? Let's see here, what happens if we take L sub A of, say, Cx plus y? What do we get? By definition, we can pull the C out. We got A times X, right? Plus A times Y, which is also known as C times L sub A of X plus L sub A of Y. Therefore, left multiplication by A is what? It is a linear transformation, right? So, in particular, it's going from Rn to Rn, right? Which means that we can talk about the matrix of a left multiplication map, all right? And so, definition, we can define M, big M, of A to be equal to the standard matrix of the left multiplication map by A. So this gives me the matrix representation, the so-called regular representation of the algebra element A. We know how standard matrices work, right? So like let's be a little bit more explicit here. We're talking about, you know, A times E1 for my first column, right? A times E2 for my second column, and so forth and so on, right? Instead of doing A here, maybe it would be good for me to do like a Z. Let me do a Z. That would be more fun. Let's do L sub Z. I oftentimes like to use A for a component, so it's probably better for me to use Z for like an arbitrary algebra element, at least at this point. So like Z times E2, da 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 da. Finally Z times En, right? So this is the regular representation of Z in A. So like, I'm tempted to digress about the algebraic properties of this, but let me just kind of like stop there, and if we need more, we'll derive more when we need it, okay? I can say, like, I could just blather on about this for a long time, so let me not do that, because it won't get us where we need to go. Let us look at an example of this, though. So example 1, perhaps the most important example, is the case of the algebra being the complex number system, R2, right? In this case, I don't use star, right? Well, let me write it. Let me write it this way. So, like, if I have x plus iy, well, let's say a plus ib times that, right? oh, I don't know. Well, anyway. So if I have this times this, I don't really write the star in this context, right? I just go, well, ax minus by plus I times, like ay plus bx, right? That's how we multiply complex numbers. The key being what? What's the thing that makes this special? Key point. Key feature, if you like. I squared is what? -1, right? That's what makes complex numbers complex numbers. All right? So, if I look at left multiplication by, say, a plus ib, acting on x plus iy, well, that gives me what I just wrote there, right? But keep in mind that our other thing here is that 1 is E1 and I is E2. That's the standard convention, like E1 being 1, 0, E2 being 0, 1, right? This is the connection. We have a plus ib, but you could also write it a comma b. This is the transference between complex notation and two component vector notation, right? Okay, so then this, if I write it as a vector, a column vector explicit, is ax minus by, right? And then bx plus ay. And can you guys tell me what the standard matrix is here? Very good. And this right here, my friends, is the matrix representation of a plus ib. What are these 2 by 2 matrices? These are the 2 by 2 matrices, all right, which are like complex numbers. So you can also get this as, 1 times a plus ib. I'm sorry, I wrote it the other way, times E1, right? So a plus ib, I'll write it up. A plus ib times E1, a plus ib times E2, right? But how's that go? That's a plus ib times 1, a plus ib times I, right? Which is a plus ib and, minus b plus ia, which of course, going back to the, column vector notation, is ab for my first column and minus ba for my second column. So I derived the standard matrix of the complex number a plus by ib in 2 different ways, right? Direct analysis of the formula, but on the flip side by this standard matrix assembly process as per usual. All right? Now, here's the thing I will not prove, but I'll just tell you, it is true that if you calculate the matrix of Z times the matrix of W, you get the matrix of ZW. And also, if you calculate the matrix of the number 1, guess what? You get the identity 2 by 2 identity matrix. And also, if you want to calculate the matrix of Z inverse, well, guess what? It's the matrix of Z inverse. I actually said something even though I didn't say something. Right? Because the inverse on the right-hand side is a well-known inversion of a 2 by 2 matrix. Whereas the inverse on the inside here is how do you find the multiplicative inverse of a complex number? Well, maybe you already know, right? Multiply by the conjugate over the conjugate, right? Times 1 over Z. So you get like Well, you guys know the drill, I hope. 1 over x plus y, iy is what? X minus iy, right? Divided by x squared plus y squared, right? That's the formula for the inverse, right? And that's why the complex numbers are pretty nice in the sense that every non-zero complex number has a multiplicative inverse, right? Complex numbers form a field. Every non-zero, it's a commutative ring in the sense like multiplication and addition work like usual, and everything non-zero has a reciprocal, has an inverse. Example 2, my next favorite example, I take the algebra to be the hyperbolic numbers, as I call them. And here you could say r plus jr. And what I mean by that is things of the form a plus bj, such that a and b are real numbers, and j squared is equal to 1.
What did you say it was?
Hyperbolic numbers. Technically, this is a particular Clifford algebra, but I call them hyperbolic numbers, mostly to offend the Clifford algebraists, but anyway, hyperbolic numbers. They may eventually win me over to their camp, but I'm not there yet. Dr. Budarez is doing his best to try to suck me into the world of geometric algebra. Well, we shall see. I mean, all of his tales, they're too fanciful to be true. I don't know. No, I'm just kidding. Anyway. So what's the matrix of a hyperbolic number? So notice here the nomenclature is that 1 is E1 again, and j is E2. So 1 is linearly independent from j. That's what this notation actually means, guys. Like this notation means that whatever I put here, they're like formally linearly independent, all right? And I just don't write the 1 in front of the r. Like you could also say that the complex number system is r plus ir if you liked. That's another way of expressing what complex numbers are. I like that notation. It's efficient. Okay, so what's the matrix here? The matrix of a hyperbolic number, I'll use A and B, A plus BJ. It's equal to, all right, 2 by 2 matrix. I do A plus BJ times 1, and then A plus BJ times J, right? Because that's times E1 and times E2. That's the standard matrix, all right? So we got what? We got A, B, and this multiplies to what? This multiplies to like AJ plus B, right? So we just get what? We get BA. So that's the representation of a hyperbolic number. Now, it turns out that 1 over x plus jy is equal to x minus jy divided by x squared minus y squared. In other words, the multiplicative inverse, there's so many trash markers up here. They're just like driving me nuts. So like, there's terms and conditions here, right? We need for what? For y not equal to what? Like plus or minus x, right? Y is plus or minus x. You're in a world of hurt. Like you cannot do that formula. So the hyperbolic numbers are not a field. There are many quote unquote zero divisors. If I plot it, it's kind of like, like a space-time diagram. So here's y equals x, and oh man, this is the bad marker. Y equals minus x, it smells like death. So like these are places with no inverses. Of course, 0 has no multiplicative inverse, but nothing on the lines y equals plus or minus x has a multiplicative inverse. Now everything else has a multiplicative inverse. And you could have forecast this by simply using like the 2 by 2 inverse formula here, right? Like A, B, B, A inverse is flip the diagonals, minus is on the off diagonal. right? So you've got a minus ba, and then divide by a squared minus b squared. That's that formula when you translate back to numbers. All right, one more example, and then I'll finally get to the calculus. My example 3. All right, enough. Example 3, I can look at the example 3, algebra. I like to call it H3. It's R plus JR plus J squared R, where J cubed is equal to 1. And here, the matrix of this thing, something like, say, A plus BJ plus CJ squared. And here again, I'm using E1 equals to 1. The multiplicative identity of the algebra, we're using E1 for that. Then this looks like A, B, C, and then the C comes up here, and then A, B, and then the B comes up here, C, A, like that. That's the regular representation of the so-called 3 hyperbolic numbers. If you prefer, it is the group algebra, the real group algebra of the cyclic group of order 3. And the hyperbolic numbers are the real group algebra of the cyclic group of order 2, if that means anything to the audience. Probably not, and that's okay. But so anyway, here's 3 interesting, debatably interesting algebras, all right? And these are endless. You can just, there's tons of these. You can come up with many more multiplications that are possible. All right, so now that we have a little bit of a sense of like what an algebra is, let's talk about what we mean by differentiability over an algebra. So notice that we already have like some context here because an algebra is Rn. So if I have a function from the algebra to the algebra again, I'm talking about a mapping from Rn to Rn, all right? So let's consider a function which goes from the algebra to the algebra again. And again, the algebra is Rn, all right? And we'll make it generic with star, right? Then so definition, if f is, let's say if f from A to A has D, F, P, a mapping from A to A, which satisfies dFP of V times W equals to dFP of V times W. And the limit as h goes to 0 of f of p plus h minus f of p minus dfp of h, all divided by norm h equals to 0, then f is a differentiable. At P. Hopefully I haven't messed up my own definition. Let's see here, I gotta be careful. So I did it for an open subset. In definition 2.75, a differential P if there exists a linear function, such that. Okay, cool. this is fine. I mean, you could make the domain of the function be smaller than the whole algebra, but for our purposes, this is fine. So how is this different than like just differentiability? Like just plain old real differentiability. What's the new thing here that wasn't present?
dfp of b times w equals dfp of b times w.
Exactly. Yeah, this right here. Now, I think that automatically gives us real linearity of the differential, but I don't really want to drive that. So let me just put a caret here to make my life easier, where dfp is, real linear. And again, I think that's redundant. I think this boxed condition actually gives us real differentiability. I mean, regular linearity, but just to be clear, I don't want to belabor it. So in other words, it's a linear map which satisfies the Frechet quotient and a condition. This condition. So like theorem, like if f from A to A is continuously real differentiable, and dfp of v, come on, dfp times w is equal to dfp of v times w for all v and w in A. Well, then f is let's say on U. Then f is a differentiable on U. I'm just kind of upping the game from a single point to like a whole neighborhood or something. Right. All right. So my larger question though is like, what does this condition mean for us? Like, what's the Jacobian of this function, by the way? So that's the standard matrix of the differential, right? But how does that work? What's the first column? Well, we know it is dfp of E1, right? And then dfp of E2, and so forth and so on, right? dfp of En. So again, for this A differentiable map, the Jacobian, the differential P, is equal to, let me rewrite that a little bit suggestively. Isn't that the same as dfp of 1 times E1? And isn't that the same as dfp of 1 times E2? And so forth and so on? What am I doing? I'm just, noticing that I can rewrite E sub j as what? As 1 times E sub j for each j, right? So what does this mean? This means that the Jacobian matrix of an A differentiable map, while it is still an n by n matrix, It's actually completely and totally governed by whatever happens to the identity. See, because once you know what happens to 1, that's everywhere, right? And so if 1 is equal to E1, this is even nicer. If 1 is equal to E1, then remember our previous discussions? What's the situation with DFP of E1? We talked about this. This is actually partial F, partial what? Remember? The first column in the Jacobian matrix is the differential fed E1. It is the first partial derivative. It's partial F partial X1 at the point. So you see in this context, the Jacobian matrix of this a differentiable function, it's given by, and I'm dropping the point dependence, guys, if that's okay. Well, I mean, what do you got? You've got partial F, partial X1, partial F, partial X1 times E2, and so forth and so on. Partial F, partial Xn times En. That's the form of the Jacobian matrix for an a-differentiable function. And so, definition, f prime of p is simply equal to dfp of 1 for f and a differentiable function. Thus, f prime is itself a function from a to a, given by what? What I just wrote, right? So we don't suffer this like meta problem of linear upon linear upon linear upon linear we did in the previous context. For a differentiable map, the derivative of an a-differentiable function is again just an a-differential, is a function on a again. And you can do this again and again and again. Like I can calculate f prime prime by the same token as we do in Calc 1, you know, like f prime prime is again a mapping from a to a, where, you know, f prime prime of p is simply the differential of f prime, yeah, the differential of f prime at p acting on 1. And by the way, this is exactly partial f partial x1 at p. And this is exactly partial squared f partial x1 squared at p. In the context that the identity is the unity, is, you know, in the case that E1 is the identity of the algebra, as it was the case for all 3 of my examples. You can't always do that. There are other algebras where you like, it's not natural to have E1 as the identity, but we don't need to talk about that today. Oops, I guess I talked about it. But this in a nutshell is what I mean by the A-calculus. Then the question, of course, becomes, okay, well, what did we learn in Calculus 1? We learned, remember, laws of differentiation. What were those laws? So this story I'm telling you, I'm relating the A-calculus to like advanced calculus, right? I'm relating the derivatives with the algebra variable to the real derivatives, and like, so that's one part of the story. But the A-calculus lives on its own. You know, it has its own existence, let's say, its own set of rules and laws and everything. And I think you'll find that those rules were rather familiar. See, because if I have 2 a-differentiable functions, right, f and g, let's say, and I calculate the derivative with respect to the algebra of their sum, care to guess how that works? So like d dz of f plus g, guess what? df dz plus dg dz. Now this one's a little bit tricky, but bleh, words. ddz of f times g, guess what? It's df dz times g plus f times dg dz. And, I mean, there's more. If you take the derivative with respect to time of f of a path in the algebra, then that's df dz times d gamma dt. And here I'm talking about gamma. I'm mapping from the reals to the algebra, a path. Whereas f is a differentiable function here. So, and I just also introduced some new notation, which you hopefully won't find surprising. F prime of z is df dz, all right? Is df sub z of 1, if you like. Now, the proofs of these laws of calculus, they all just rest on things we know about differentials. Like that Uber product rule I proved the other day. You know, essentially, if we take the differential, oh, come on. If I take the all right, okay, this one works, yay. The differential of f times g, right, at p acting on 1 is equal to partial x1, right, of f times g. But we proved the Uber product rule. And the Uber product rule said that, hey, this is partial f partial x1, right, at the point, times g at the point, plus f at the point, times partial f, my bad, partial g partial x1 at the point, right? Which, by the way, is dfp at 1 times g of p plus f of p times dgp of 1, which, of course, is f prime of p times g of p plus f of p times g prime of p. All right, I think so my Uber product rule proves the product rule holds on the algebra, because of course this is f times g prime of p, right? So here's the missing problem. The missing problem in your homework, the last one, I wanted you guys to, this should be like a super easy problem if I can state it correctly. Hopefully this one, it's going to involve a square again, but this will hopefully not be a repeat of my first attempt at a squared homework problem. This one's going to be nice. So problem 16, I want you to look at f of z is equal to z squared. Of course, z squared in this context would mean z times z, right? And show f prime of z is equal to 2z. Okay. I've almost done that here, but like, I suppose you need to, I suppose the one thing you probably need to, suggestion, start by convincing yourself that you can show this is true. ddz of z is equal to what?
1.
1, right. But that is, that's not known. You need to show that. Right, so like look at the function f of z equals to z and work through how that works. So like here, we can think about z as like x1 e1 plus, you know, x2 e2 plus dot dot xn en, because I want you guys to try to understand this for an arbitrary n-dimensional algebra. So when I write z, I'm writing it as a n vector, which has components x1, real components x1 through xn, right? So well, anyway, I'm going to let you guys see if you can sort through it. If you get stuck on something, just come talk to me. It's not... Listen, if you get totally stuck, just say, I can't quite figure it out, but this has to be true. You told me. And I'm going to use this and other things to prove this. Okay, yeah. So I discovered this A calculus working with some students like 2011-ish, right? And it started with a student named Min asked me he wanted to do an independent study of linear algebra over the summer for reasons I forget. I was like, okay, and then Min's like, can we write a paper in linear algebra? And I'm like, no. I'm not a linear algebraist. Like, I like linear algebra. I know a little bit about it, but certainly not research level. But I know what I know, which was supermath. And so I was like, but if you want to, we look at my thesis topic, and maybe if we do that for a little bit, we can find something in there that, suits your interests, and we can dig into that and maybe, do something there. So let's kind of look at what I know. And then in the process of trying to explain to him my thesis topic, we stumbled upon much more basic questions like, like what would it mean to have a multiplication, on an algebra, like a finite dimensional algebra. My thesis sort of deals with an infinite dimensional algebra. And really just one example. So like my thesis is on something that's much more technical, but also far less broad. So this is very broad, but not as technical. And so I like it for undergraduates because really you just need to know like linear algebra, calculus 3, and then you can start trying to do things like do differential equations over these algebras, things like that. Like for example, we could define e to the z as like 1 plus z plus 1/2 z squared. There's a theory of series. It all works out. Now the convergence, divergence stuff for series, it's quite horrible. The zero divisors plays havoc. It destroys all of your usual divergence results. The convergence stuff still kind of works, but the divergence stuff falls away. But long story short, you can use any of the power series you saw in Calculus 2. You can use those to define functions on the algebra. So I can talk about exponential, sines, cosine, coshs, sinches. That's all there. And they all satisfy the usual calculus, as long as it's commutative algebra. So like, for example, in the complex numbers, it's well known that e to the x plus iy is e to the x times e to the iy, which is equal to e to the x cosine y plus I e to the x sine y. So this would be an example of a, e to the z. So check this out. d dz of e to the z, right? If you believe what I told you today, the complex derivative is the derivative with respect to the first coordinate function for a complex differentiable map. The exponential is complex differentiable. So that means that this is just partial x of this. What happens when you hit an x derivative on that? Like nothing, right? So, yeah. Which means that the derivative of the exponential is, the exponential. Let's look at something a little more interesting. let's do, now this is not your homework, but it's like your homework, z squared. In the complex case, the z squared is what? So I'm telling you that's really partial x of x plus iy times x plus iy, which is what? We've got x squared. Yeah, there's a, yeah, minus y squared plus 2ixy, yeah. Take the x derivative of that, what do you get? 2x plus 2iy, also known as 2z. So, like, is this the right way to do derivatives over an algebra? Like, always convert back to the real component functions and differentiate with respect to the first one? No, absolutely not. I'm just trying to make it more familiar. You understand x partial derivatives, right? You don't probably understand ddz because you haven't had the complex variables course, right? Are you guys going to take complex variables? Probably not? No. Last semester. It's unfortunate. If there's any kind of more abstract math that ought to be required, besides linear is important obviously, but like for engineering, complex is actually very eye-opening. Computationally, it has many, many things that it would be good for you guys to see. Ah, so you've seen some things then, good. Now, one of the things I want to point out, so like, I think I just erased it, but if you look at what we had that partial f, partial xj was equal to partial f, partial x1 times ej. All right? And there's like a, let me just kind of get to the point here. I wanted to tell you guys a thing. So if you fiddle around with this a bit, what you eventually learn is that the nth derivative of f with respect to like partial xi1, partial xi2, partial xin. Suppose you take the derivatives with respect to this n tuple of coordinates. All right, so like that. Well, that's the same as simply taking the n-fold derivative. And it's unfortunate I've used n here. Maybe let me switch this up for a k. Because I've used n to mean the dimension of the algebra, and that has nothing to do with what I'm saying. Okay, so let's make that a k. So I1 through ik. Well, that's the same as taking the kth derivative with respect to the first variable, the identity variable. Again, this is all in the context that E1 is the identity of the algebra. That times let's see here, EI1, EI2, EIK. What this means is that partial differentiation is like completely tied to just multiplication in the algebra. A practical application of this is that in the complex numbers, I squared plus 1 is equal to 1 squared is equal to 0. When you understand this, what's downstream of that is saying that the yy derivative of f plus the xx derivative of f is equal to 0 for a complex differentiable function. And that's a complex equation, so that actually is true for both the real and the imaginary components of the complex function. They're both what are called harmonic functions. They're both solution to Laplace's equation. But in the hyperbolic numbers, this identity is true. J squared minus 1 is equal to 0. And for a hyperbolic differentiable function, in fact, we have fyy minus fxx is equal to 0. This is what I would call the Laplace equation, or the A Laplace equation.